In the time it takes to watch this video, light from the most distant known galaxy will race another 300 million miles closer to us. That journey began when the universe was only 280 million years old, long before Earth formed, before the Sun was born, before the Milky Way became what it is today. Now, we'll soar through all 2 trillion galaxies in the observable universe. You'll witness colossal collisions unfolding across hundreds of millions of years, encounter galaxies that defy the laws of physics, and see structures so vast they reduce our Milky Way to a grain of dust. If you're ready to stretch the boundaries of your cosmic imagination, tap the like button and let's begin our journey. Almost everything you thought you knew about the number of galaxies is off by tenfold. For years, astronomers were certain our observable universe held around 200 billion galaxies. That figure already felt unfathomable. But then came the James Webb Space Telescope, peering with its infrared vision into patches of sky that looked completely empty. The result shattered our expectations. The real number isn't 200 billion. It's closer to 2 trillion. For every galaxy we thought existed, 9 more were hidden. Too dim, too distant, until Webb revealed them. Pause on that thought. With every blink of your eye, light from thousands of these galaxies advances another mile on its journey to us. Many of those photons began traveling before our solar system was even born. What we're seeing are the baby pictures of the cosmos, and the nursery is far more crowded than anyone imagined. The first hints came from Hubble's ultra-deep field. To capture it, Hubble took 800 exposures over 11 days, focused on a patch of sky no larger than a grain of sand held at arm's length. Out of that apparent emptiness, 10,000 galaxies appeared. 10,000 entire worlds of stars, in a sliver of sky so small it could hide behind the dot at the end of this sentence. But here's where things turn staggering. That single image represents just 1/13 millionth of the sky. Multiply it out, and suddenly the numbers explode. Even then, Hubble only saw the nearby and the bright. Webb went further, catching galaxies so distant their light stretched into the infrared, and so faint they're like spotting a candle on the moon. Yet each one contains hundreds of millions, even trillions, of stars and planets, and maybe, just maybe, civilizations we'll never encounter. At this scale, math starts to lose meaning. If every galaxy held as many stars as the Milky Way, about 100 billion, we'd be staring at roughly 200 sextillion stars. That's a 2 followed by 23 zeros. More stars than every grain of sand on Earth's beaches combined. And still, that's only within our observable bubble. Beyond the horizon, the universe continues, possibly forever, with galaxies stretching endlessly in every direction. What we see is just the foam at the edge of an infinite ocean, and yet numbers alone can't capture the truth. Because inside each galaxy lies drama, creation, destruction, beauty, and violence on unimaginable scales. Right now, as you hear these words, you're flying through space at over 1 million miles per hour. You don't feel it, but you are not only spinning on Earth, not only circling the Sun, but being carried along by the Milky Way itself as it speeds through the cosmos. And we are not adrift alone. Our Milky Way is part of the Local Group, a gravitational family of over 50 galaxies, each locked together in an ancient dance spanning 10 million light-years. Picture this. If the Milky Way were the size of a dinner plate, our Local Group would stretch all the way from New York to Los Angeles. And at the heart of this vast neighborhood, 3 titans dominate. Among them, the Andromeda Galaxy, home to more than 1 trillion stars, a leviathan stretching 220,000 light-years from edge to edge. Andromeda, roughly twice the size of our own Milky Way, is heading directly toward us at a speed of 68 miles per second. The collision is certain, scheduled for about 4.5 billion years from now. But that cosmic catastrophe is a story for later. For now, our Milky Way holds second place in the hierarchy of the Local Group, home to an estimated 300 billion stars stretched across a disk 100,000 light-years wide. Our solar system lies about 26,000 light-years from the galactic center, tucked safely inside the Orion Arm, one of the graceful spiral branches that give our galaxy its iconic pinwheel form. The third great power in our neighborhood is the Triangulum Galaxy. Smaller, yes, just half the size of the Milky Way, but still containing some 40 billion stars. What makes it extraordinary is its energy. Triangulum is forming new stars at nearly twice the rate of our own galaxy, blazing with stellar nurseries. These three giants are surrounded by a retinue of smaller companions. Dozens of dwarf galaxies orbit them like loyal satellites. Around the Milky Way itself, the largest of these are the Large and Small Magellanic Clouds, visible from the southern hemisphere as faint glowing patches in the night sky. The large cloud contains around 30 billion stars, while its smaller sibling hosts roughly 3 billion. But even this structure, our entire local group, is itself only a single thread in an unimaginably vast web. We reside at the edge of the Laniakea supercluster, a sprawling assembly of over 100,000 galaxies spread across 520 million light-years. The name comes from Hawaiian, meaning immense heaven, and it is quite literally our cosmic address. And all of these galaxies, including our own, are not standing still. They're streaming like rivers of light toward a mysterious gravitational anomaly known as the Great Attractor. Located about 250 million light-years away, this cosmic leviathan carries the mass of tens of thousands of galaxies, pulling our entire supercluster toward it at over 1,000 miles per hour. Yet at the same time, the expansion of the universe drives most galaxies away from us, like islands retreating on an inflating ocean. It is a paradoxical journey, part drift, part pursuit. But the calm appearance of our cosmic neighborhood hides a violent truth. The Milky Way is not a peaceful giant, it is a predator. For more than 10 billion years, it has been devouring smaller galaxies to grow larger and stronger. Even now, this galactic cannibalism continues. The Sagittarius dwarf galaxy, a fragile neighbor, is being torn apart by the Milky Way's gravity. Its shredded remains form vast stellar streams wrapping around our galaxy like ribbons of light. Another victim, the Canis Major dwarf galaxy, was so completely destroyed that its remains were only discovered in 2003. This process is anything but gentle. Imagine a whirlpool dragging a small boat into its current. That is what happens when a dwarf galaxy drifts too close. Its stars are stretched, twisted, and ripped free, either captured by the Milky Way's halo or cast adrift forever into the darkness between galaxies. Astronomers can still trace the identities of these lost galaxies. Each star carries a fingerprint in its chemistry. By comparing the heavy elements in their light, scientists can distinguish stars born in the Milky Way from those stolen from neighbors. It's cosmic forensics, solving ancient crimes written in starlight. But even destruction has its gifts. The death of Sagittarius is igniting life within the Milky Way. As its gas clouds collide with the Milky Way's disk, they spark waves of star formation, vast nurseries where countless suns are being born. In a strange irony, one galaxy's death is fueling the rebirth of another, and soon, the Large and Small Magellanic Clouds, our most luminous companions, will be next on the menu. The Large and Small Magellanic Clouds, visible to the naked eye from Earth's southern hemisphere, lie about 160,000 light-years away. But these companion galaxies are not in stable orbits. Astronomers have confirmed they are on a collision course with the Milky Way, destined to be swallowed whole within the next 2 billion years. When the Large Magellanic Cloud finally merges with our galaxy, the event will be extraordinary. The collision will ignite massive waves of star formation, set the night sky ablaze with radiant nebulae, and may even awaken the supermassive black hole at the heart of the Milky Way, transforming it into a quasar brighter than entire clusters of galaxies. But galactic cannibalism is not unique to us. Andromeda, our nearest giant neighbor, has been far more ruthless. Astronomers have identified the shredded remains of at least 10 dwarf galaxies scattered across its outer halo, most consumed within the last few billion years. Their ghostly trails still hang across space, faint rivers of stars stretching for hundreds of thousands of light years. This is no accident. It is the universal pattern. Larger galaxies grow by devouring smaller ones, which themselves once consumed even tinier systems. The cosmic food chain has been unfolding since the first galaxies formed more than 13 billion years ago. But all this pales before the ultimate collision that awaits us. In roughly 4.5 billion years, the Andromeda Galaxy will crash into our own. Even now, it is racing toward us at 68 miles per second. That may not seem fast compared to light itself, but on the scale of galaxies, it is 2 titanic freight trains sharing a single track. The impact is inevitable, and it will reshape both galaxies in the most violent event this corner of the universe has ever seen. For decades, Astronomers wondered if Andromeda would strike us directly or drift past in a near miss. That uncertainty ended in 2012, when the Hubble Space Telescope precisely measured its sideways motion. The result was clear and terrifying. Andromeda is aimed straight at the Milky Way's heart, yet a galactic collision is nothing like two solid bodies smashing together. Galaxies are mostly empty space. Stars are separated by distances so vast, about 25 trillion miles on average, that almost none will collide head-on. Instead, the real drama comes from gravity. As the two giants approach, their outer edges will stretch and twist under immense tidal forces. Whole star systems will be slingshotted into the dark void between galaxies, ripped away from their homes and cast adrift. Some will carry planets with them, entire solar systems left to wander intergalactic space, orphaned and alone. At the same time, the two supermassive black holes at the cores of both galaxies will begin a slow, spiraling dance toward each other. The Milky Way's black hole holds about 4 million solar masses, but Andromeda's dwarfs it, containing nearly 100 million. When they finally merge, they will unleash gravitational waves so immense they will ripple across the fabric of the universe, detectable by civilizations billions of light years away. And while destruction unfolds, creation will surge. The collision of gas clouds from both galaxies will ignite the birth of new stars at a rate 10 times faster than what we see today, lighting up the sky with spectacular brilliance. The merged galaxy will blaze with newborn suns, a cosmic fireworks display spanning millions of years. The fate of Earth in this grand event is uncertain. Simulations suggest there is about a 50% chance our solar system will be pushed outward, 3 times farther from the galactic center than we are today. There is also a smaller but real chance, around 12%, that we will be ejected entirely, sent drifting into the cold expanse between galaxies. And yet, here is the most mind-bending possibility of all. If humanity endures long enough to witness the beginning of this collision, our distant descendants will watch the night sky transform across countless generations. An epic, slow-motion cosmic ballet, with front-row seats to the greatest light show the universe has to offer. The night sky will one day blaze with new stars as Andromeda draws nearer, swelling brighter until its spiral of fire dominates the heavens from horizon to horizon. When the chaos finally settles, the Milky Way and Andromeda will merge into a colossal elliptical galaxy, already given the name Milkomeda by astronomers. It will outweigh either of its parents by nearly tenfold, ranking among the giants of our local supercluster. Yet even this titanic collision feels small beside stranger cosmic tragedies, galaxies that have already died in ways that should not be possible. Some have been lifeless for billions of years, and no one knows why. Take Max 21291. From afar, it looks like a normal spiral galaxy, more massive than the Milky Way and spinning nearly twice as fast. But a closer look shattered every model of galaxy evolution. This galaxy stopped forming stars over 10 billion years ago. It is, in essence, a cosmic zombie. Frozen in time, its beauty preserved, but its life extinguished. Dead galaxies, often called quenched galaxies, are places where starbirth has come to a halt. Normally, vast clouds of gas and dust collapse into new stars, a cycle that should last trillions of years before cosmic expansion drains galaxies of their fuel. But Max 21291 broke the rules. Somehow, while the universe was still young, it lost or expelled every trace of star-forming material. For small galaxies, this kind of death is not so surprising. A nearby supernova or the pull of a massive neighbor can strip away their gas. But for a galaxy this large, with gravity strong enough to cling tightly to its fuel, such a fate should be impossible. Stranger still, most dead galaxies we've found are ellipticals, the result of violent mergers that scramble their spiral arms into formless clouds. Max 2129-1, however, kept its elegant spiral structure intact. It is like a perfectly preserved mummy, beautiful on the outside, lifeless within. Spectroscopic studies show its stars did not come from catastrophic mergers, but from steady, ordinary star formation long ago. Then something unknown silenced it almost overnight. Some theories suggest its central black hole erupted with such fury that it blasted surrounding gas into oblivion. Others imagine a chain reaction of supernovae that blew its reserves into the void. But the most unsettling idea is that we are missing a fundamental truth about how galaxies live and die. An unknown process that can kill even the mightiest spirals without warning. And Max 21291 is not unique. Astronomers have found dozens of massive spiral corpses scattered across the deep universe, each billions of years too old for death. Everyone adds another fragment to a puzzle that only grows darker, stranger, and more urgent the more we look. Dead galaxies are only the beginning of the strangeness hidden across the cosmos. Some galaxies are being ripped apart so violently they look like living creatures drifting through the void. Cosmic jellyfish swimming in a sea of stars. One of the most haunting examples is ESO 137 located about 220 million light-years away. At first glance, it resembles an ordinary spiral, but closer inspection reveals the truth. This galaxy is drowning. Vast trails of gas and stars stream behind it, like glowing tentacles, stretching for nearly 200,000 light-years. The cause is a brutal process known as ram pressure stripping. Imagine racing down a highway in a convertible during a storm. The rushing wind rips the rain right off your windshield. Now magnify that to galactic scales. ESO 137 is hurtling through the Perseus cluster at over 1,000 miles per second, smashing into clouds of superheated gas that fill the space between galaxies. To us, that gas would feel like a perfect vacuum. But at such speeds, it's like hitting a wall. The galaxy's own lifeblood, its star-forming gas, is being peeled away layer by layer. Those luminous tentacles glimmer because young stars are still forming within the stripped material, glowing blue against the darkness like embers torn from a fire. But the process is irreversible. Once the gas is gone, the galaxy cannot replace it. Its massive stars will burn out and explode, leaving only faint red dwarfs to flicker across the ages until the galaxy fades into a ghost. Dozens of jellyfish galaxies have been discovered, each caught in a different stage of this slow-motion destruction. Some are just beginning to lose their outer gas, while others are already reduced to ragged filaments adrift in space. Hubble images reveal long contrails of newborn stars stretching across distances larger than our entire local group. It is cosmic beauty born from violence, spirals twisted, arms compressed, bursts of star formation igniting just before the light goes out forever. These galaxies are breathtaking, their glowing tendrils resembling works of art painted across the void. But every luminous streamer marks the death of a stellar city that once may have carried billions of worlds. And still, as tragic as they are, even jellyfish galaxies are not the strangest things we've found. Because somewhere out there is a galaxy that should not exist at all. A galaxy without dark matter, a skeleton without bones. And its very presence is rewriting what we think we know about the universe itself. Dark matter makes up about 85% of all the matter in the universe. It's the invisible scaffolding that allows galaxies to form, spin, and survive. Without it, galaxies should fly apart or never form in the first place. And yet there it sits, NGC 1277, a galaxy seemingly held together by nothing more than the gravity of its visible stars. When astronomers announced this discovery in 2018, it shook the foundations of modern cosmology. For decades, dark matter has been considered one of the fundamental pillars of our understanding of the universe. We can't see it, we can't touch it, and we don't know what it's made of. But we know it's there because of its fingerprints, the way it binds galaxies, sculpts clusters, and weaves the great cosmic web. Without dark matter, the universe we know simply shouldn't exist. And yet NGC 1277 defies this. It's what astronomers call a relic galaxy, a survivor from the early days of the cosmos. It's several times more massive than the Milky Way, yet packed into a much smaller space, making it astonishingly dense. But measurements reveal the unthinkable. No surrounding halo of dark matter, just stars. At first, astronomers questioned the data. Perhaps the galaxy was closer than it appeared, skewing the measurements. Perhaps it had once possessed dark matter, but was stripped bare by the gravitational tides of nearby giants. Yet follow-up observations confirmed it. NGC 1277 truly is a massive galaxy, almost entirely devoid of dark matter. The implications are staggering. One idea is that it formed in a rare way, where normal matter separated from dark matter at birth, possibly due to extreme conditions in the early universe. Another possibility is that the Perseus cluster, the massive cosmic city where NGC 1277 resides, tore its dark matter halo away while leaving the stars intact. But the most unsettling explanation is that our entire concept of dark matter might be flawed. Maybe what we call dark matter is really a modification to the laws of gravity themselves, a hidden rule of physics that doesn't always apply. If that's true, then NGC 1277 could be a glimpse of what galaxies look like when those hidden rules vanish. It forces astronomers to ask dangerous questions. Are there other galaxies like this? Could vast regions of space exist without dark matter at all? And if so, what does that mean for the story of how the universe formed? NGC 1277 is a cosmic anomaly, an object that shouldn't exist, yet does. A galaxy without bones, standing in defiance of everything we thought we understood about reality. And if that seems impossible, just wait. Because astronomers have also discovered galaxies where the gas itself glows brighter than the stars. Objects so strange, they've been called an entirely new kind of phenomenon. One such galaxy, GS-NDG 9422, was born when the universe was less than 1 billion years old, and what scientists saw in its light had never been seen before. In most galaxies, stars are the brightest engines of light, nuclear furnaces burning at millions of degrees, flooding space with energy. The gas between them, while essential for new star birth, usually glows faintly in comparison. But in a galaxy known as GS-NDG 9422, this balance is completely inverted. Here, the gas itself blazes brighter than the stars. Its clouds are superheated to more than 140,000 degrees Fahrenheit, nearly twice as hot as the surfaces of massive stars. At these extremes, the gas radiates so intensely that it outshines the very stars that should be powering it. When the James Webb Space Telescope first captured its light, astronomers saw something no one had ever seen before, a signature of ionized gas stripped of electrons, demanding an energy source far beyond what ordinary stars could provide. It was like discovering a pot of water boiling furiously over nothing more than a candle flame. Something else was at work, something far more powerful. Models suggest this galaxy harbors primordial stars vastly hotter and more massive than anything that exists today. Their ultraviolet radiation could have been strong enough to transform the early universe itself. This discovery may be the missing link to one of cosmology's greatest mysteries: how the dark, opaque universe of neutral hydrogen gave way to the transparent star-filled cosmos we see today. For decades, scientists suspected the first stars rionized the universe, but ordinary stars didn't produce enough radiation to do the job. GS-NDG 9422, with its superheated gas and monstrous stellar population, might finally provide the answer. It also hints that the early cosmos was far more violent and chaotic than we imagined, a place where stars lived short, explosive lives and galaxies burned with impossible energy. And most intriguingly, it may be our first glimpse of the long-theorized population 3 stars, cosmic giants hundreds of times the mass of our Sun, blazing into existence before burning out in cataclysmic deaths. Yet even this bizarre galaxy seems almost tame compared to what James Webb has found next. Enormous systems so massive, so impossibly early, that they defy every model of how the universe should have unfolded. These are the red monsters, galaxies as heavy as the Milky Way, already fully formed when the universe was less than 1 billion years old. They glow with a deep red hue, their light filtered through enormous amounts of cosmic dust. This dust acts like a veil, absorbing the harsh blue and ultraviolet radiation from the stars and re-emitting it in the infrared spectrum. But the very presence of such dust in these ancient galaxies poses a mystery of its own. Dust grains form only after multiple generations of stars live, die, and scatter heavy elements into space. So how did galaxies in the infant universe already accumulate such vast dust reservoirs so quickly? The standard picture of galaxy formation describes a slow and steady process. Tiny clumps of dark matter gradually merge together, pulling in gas over billions of years until they finally become massive enough to give birth to galaxies like the Milky Way. Yet, these red monsters seem to have compressed that entire evolutionary story into less than 1 billion years. Even more puzzling, they are forming stars at nearly double the rate of galaxies of similar mass today, suggesting that star birth in the early cosmos was far more efficient than theory allows. The discovery came from the FRESCO survey, which uses Webb's near-infrared camera paired with a spectrograph to measure the distances and masses of early galaxies. Out of hundreds examined, 3 galaxies stood out, far larger, denser, and redder than any others. They immediately demanded explanation. The data showed that these galaxies were converting an unusually high fraction of their available gas into stars, defying the normal checks and balances of cosmic physics. In typical galaxies, exploding supernovae and radiation pressure from massive young stars act like regulators, blasting away much of the gas before it can collapse into new stars. This feedback mechanism keeps galaxies from becoming too massive too quickly, but the red monsters had somehow bypassed this cosmic safety valve. They managed to cling tightly to their gas supplies and churn them into stars with staggering efficiency, as if a factory were running at double capacity with none of the breakdowns that should normally shut it down. The implications ripple far beyond these 3 objects. If such galaxies could exist less than 1 billion years after the Big Bang, then conditions in the early universe must have been fundamentally different from what we see today. Perhaps the intergalactic medium was denser, allowing galaxies to gather material more easily. Perhaps supernova feedback mechanisms were weaker or operated differently. Or perhaps, most unsettlingly, our entire understanding of dark matter and galaxy formation is missing crucial ingredients. Each of these galaxies contains around 300 billion stars, comparable to the entire Milky Way. Yet, they pack this stellar population into volumes much smaller, creating stellar densities thousands of times greater than what we observe locally. Researchers now describe this as the too many, too massive problem. Not only are these individual galaxies far larger than expected, but they are far more common than our models predict. Early massive galaxies were supposed to be exceedingly rare, yet Webb is finding them across the sky. This abundance is forcing astronomers to rethink the basic script of cosmic history. And yet, even these red monsters seem almost modest compared to the most extreme discovery of all, the most distant galaxy ever seen. Designated MMZ14, this object represents the ultimate time machine. Its faint light left the galaxy when the universe was only 280 million years old, barely 2% of its current age. That light has been traveling for more than 13.5 billion years, carrying with it a snapshot of a cosmos just awakening from its long darkness. The galaxy's nickname, the mother of all early galaxies, comes from the fact that it pushed the record for cosmic distance back by another 20 million years. In the early universe, such a span is enormous, representing a significant fraction of the time since the Big Bang itself. Capturing MMZ14 required pushing the James Webb Space Telescope to its limits. Even with Webb's extraordinary sensitivity to infrared light, the galaxy appears as just a few faint pixels against the deep background of space. Yet within those pixels lies the most ancient light humanity has ever observed. Its distance corresponds to a redshift of Z-Pans 1444, making it the farthest known object in the universe. Redshift is the key to unlocking just how far back in time we are looking. It measures how much the expansion of the universe has stretched the light from distant objects. A redshift of 1444 means that the wavelengths of light from this galaxy have been stretched more than 15 times, pushing even its ultraviolet glow deep into the infrared, light that only Webb is sensitive enough to capture. But MMZ14 is remarkable not only for its distance. It is astonishingly massive and luminous for such an early moment in cosmic history. Containing several 100 million times the mass of our Sun, this galaxy is squeezed into a compact region only about 1,600 light-years across, tiny compared to modern galaxies. Within that compact volume, it appears to be undergoing a furious burst of star formation, producing new suns at a pace that could build the equivalent of our solar system every few years. This intense activity generates torrents of ultraviolet radiation, powerful enough to carve out a transparent bubble in the surrounding fog of neutral hydrogen that still filled most of the universe at the time the discovery of MMZ14 came through. The aptly named Mirage, or Miracle Survey. The survey was designed to separate genuine ancient galaxies from imposters, nearer galaxies whose light had been reddened by dust, masquerading as distant objects. The survey earned its name because bright galaxies at such extreme distances would either be a mirage produced by observational error or a miracle that reshapes our understanding of cosmic history. MMZ14 turned out to be the latter. Spectroscopy confirmed its enormous redshift, and even more surprisingly, revealed the presence of heavy elements such as oxygen. That meant multiple generations of massive stars had already lived and died by the time we are seeing this galaxy. Star formation, therefore, must have begun far earlier than theory had allowed. Its existence forces profound questions. According to standard cosmological models, it should have taken much longer for dark matter halos to grow massive enough to host such a luminous galaxy. Yet here it is, blazing into existence just 280 million years after the Big Bang. The evidence suggests that galaxy formation in the early universe was far more efficient, or that unknown physical processes were at work during this primordial era. Perhaps most staggering is the realization that MMZ-14 sits at the dawn of cosmic reionization. This was the pivotal moment when the first stars and galaxies began to lift the universe out of its dark ages, ionizing the hydrogen fog and making space transparent to light for the first time. We are witnessing one of the first lanterns in a cosmos that had been almost entirely dark. But MMZ-14 is not alone. It is one of many early galaxies now appearing in Webb's data, each of them rewriting our understanding of the universe's infancy. Every photon that reaches us from these galaxies is a time traveler, crossing more than 13 billion years of cosmic history to deliver a message from an era when the universe looked nothing like it does today. Our eyes cannot see. Space was filled only with neutral hydrogen and mysterious dark matter. If you could somehow stand in that ancient void, even the brightest flashlight would fail to pierce the blackness. Yet in that darkness, gravity was quietly at work. Tiny ripples in the density of dark matter, seeded during cosmic inflation, slowly grew. Over millions of years, they became halos massive enough to draw in clouds of hydrogen gas. These halos provided the cradles for the very first stars. This first generation, known as population 3 stars, was unlike anything we see today. With no heavy elements available, only the hydrogen and helium forged in the Big Bang, these stars grew to titanic masses, hundreds of times greater than the Sun. They burned at scorching temperatures, synthesizing the very first carbon, oxygen, and iron. But they lived brief and violent lives. Within just a few million years, they exploded as hypernovae, seeding the cosmos with the raw materials for all future stars and planets. That enrichment allowed the second generation of stars to form, stars with more diverse chemistries, and these began to cluster into the first true galaxies. Webb's extraordinary infrared eyes are now giving us our first glimpses of these ancient systems. Fossils from over 13 billion years ago, preserved in light that has only now reached us. And what the telescope is revealing is a universe far more turbulent, far more chaotic, and far more alive with violent activity than astronomers ever expected. The earliest galaxies that Webb has uncovered are larger, more active, and far more common than our best theories ever allowed. Their star formation rates are off the charts, suggesting that the first billion years of cosmic history were an era of astonishingly rapid and efficient galaxy building. But the light from these primordial systems carries more than just the story of stars. It holds the fingerprints of one of the most important transitions in the universe's history: cosmic reionization. When the first stars ignited, they poured out ultraviolet radiation that began stripping electrons from neutral hydrogen, turning the fog of the early cosmos into a transparent medium. For the first time since the cosmic microwave background was released, 380,000 years after the Big Bang, the universe became visible. This transformation did not happen all at once. It began locally, around the most massive galaxies, and then spread outward like bubbles of light in a sea of darkness. Those bubbles expanded, merged, and eventually cleared the entire cosmos. Webb is now able to trace this grand change, mapping how the light from distant galaxies is absorbed by hydrogen still waiting to be ionized. Piece by piece, the telescope is reconstructing the very moment when the universe awoke. And what we are learning is astonishing. The transition from darkness to light happened faster, fiercer, and more dramatically than anyone had predicted. In less than 1 billion years, the universe went from a place of total darkness to a cosmos blazing with massive galaxies. It was a cosmic dawn, as sudden as it was transformative, an event that reshaped the destiny of everything that followed. Yet these first galaxies were not the end of cosmic violence. They were only the opening act. Entire regions of space would soon be reshaped by collisions on scales so vast they defy human comprehension. One of the most spectacular examples lies 68 million light-years away, where two galaxies have been locked in a death spiral for over 600 million years. We know them as the antennae galaxies. Their name comes from the enormous tidal tails stretching outward from their hearts, resembling the antennae of some strange cosmic insect. But these structures are not delicate filaments. They are streams of stars, gas, and dark matter violently ripped from their parent galaxies. Their beauty masks unimaginable destruction. The collision began when two elegant spiral galaxies, once ordered and serene like our own Milky Way, drifted close enough for their mutual gravity to entwine them. What followed was an inexorable distortion. Their perfect shapes unraveled. Stars were flung into colossal streamers that today span more than 200,000 light-years, and gas clouds crashed into one another, triggering furious bursts of new star formation. It is almost impossible to grasp the scale of this violence. Each galaxy contains hundreds of billions of stars, and all of them are being accelerated, tugged, and hurled about by gravitational forces millions of times stronger than anything our solar system will ever know. What looks serene in the telescope's eye is, in reality, a titanic ballet of destruction. The earliest galaxies turned out to be far more massive, far more active, and far more numerous than our models had ever suggested. Their rates of star formation were off the charts, reshaping our understanding of the first billion years of cosmic history. This was a time defined by rapid, almost explosive, galaxy assembly. The light that traveled from these ancient systems carries with it the memory of cosmic rionization. As the first stars ignited, they poured ultraviolet radiation into the universe, stripping electrons from neutral hydrogen atoms and gradually making space transparent for the very first time since the release of the cosmic microwave background some 380,000 years after the Big Bang. This wasn't a uniform process. Rionization began around the most massive galaxies, carving out great bubbles of ionized gas that expanded and merged until they encompassed the entire cosmos. By analyzing the way distant starlight is absorbed by clouds of neutral hydrogen, telescopes like Webb allow us to map this extraordinary transformation. Piece by piece, every newly discovered galaxy from the cosmic dawn adds to this grand puzzle. We now know that the transition from darkness to light happened faster and more violently than anyone expected. In less than 1 billion years, the universe leapt from complete obscurity to blazing brilliance. A transformation, among the most important in the history of everything. But the story of galaxies has always been one of both creation and destruction. Two particular galaxies have been locked in a violent gravitational embrace for over 600 million years, and we are witnessing their final act. They are known as the antennae galaxies, NGC 4038 and NGC 4039, located about 68 million light-years away in the constellation Corvus. Their name comes from the immense tidal tails that sweep out from their cores, like the delicate feelers of an insect. Yet these trails are anything but delicate. They are colossal streams of stars, gas and dark matter, violently torn from their home systems by gravity on a scale we can scarcely imagine. The collision began when the two spiral galaxies first drifted within reach of each other's pull. Each was once a well-ordered spiral, perhaps not unlike our own Milky Way. But gravity twisted their shapes, flinging stars and gas into arcs that now span more than 200,000 light-years. Hundreds of billions of stars are being accelerated, scattered, and redirected by forces millions of times stronger than anything within our solar system. Some stars have been ejected entirely, set adrift into the void, doomed to wander intergalactic space alone for billions of years. Yet within this chaos, creation flourishes. Where gas clouds from the colliding galaxies smash together, they compress and ignite bursts of furious star formation. The antennae system is giving birth to new stars at a rate nearly 10 times higher than that of typical galaxies. Brilliant blue and pink patches shine across the collision zone. The blue reveals clusters of hot young stars flooding space with ultraviolet light. The pink marks glowing clouds where that light strikes nearby gas, igniting them like vast cosmic neon signs. The Hubble Space Telescope has shown us that some of these regions contain the largest star clusters ever observed on sprawling metropolises of millions of stars, packed into areas just a few dozen light-years across. Had Earth been placed near one, our night sky would blaze with thousands of points brighter than Venus. Simulations reveal that the antennae have not yet reached their peak violence. Over the coming hundreds of millions of years, their cores will spiral inward, triggering waves of even more intense star formation. In time, their central supermassive black holes will merge, releasing gravitational waves across the cosmos. The final product will be a single giant elliptical galaxy, larger, older, and quieter than either of its spiral ancestors. This metamorphosis, from spirals to ellipticals, is one of the fundamental engines of cosmic evolution, and the antennae are a rare chance to watch the process unfolding in exquisite detail. Astronomers can study how star formation changes across the collision, track the growth of new clusters, and even detect supernovae erupting within the maelstrom. But the antennae are not only a spectacle of the present, they are a prophecy of our own future. In about 4.5 billion years, the Milky Way will merge with Andromeda in a dance every bit as violent and spectacular. The physics will be the same, only the scale will be grander. And yet even this is not the largest act of cosmic violence. In galaxy clusters, entire populations of galaxies undergo a slower torment known as galactic harassment. Unlike intimate mergers, harassment is a relentless series of high-speed encounters that chip away at smaller galaxies, warping and stripping them over billions of years. The Coma cluster, 320 million light-years away, holds over 1,000 galaxies crammed into a space just 20 million light-years across. To human imagination it might sound spacious, but on cosmic terms it is suffocatingly dense. Each galaxy is pulled, battered, and reshaped by the gravity of its neighbors. Think of a sandcastle standing on a beach during a hurricane. Each crashing wave doesn't destroy it outright but slowly erodes it, grain by grain, until nothing remains. That is the fate of countless galaxies in such clusters. The waves, in this case, are the gravitational tides of passing giants, and the castles are the fragile star systems that crumble under their power. Spiral galaxies, like our own Milky Way, suffer the most in these violent environments. Their graceful arms and wide gas disks are fragile, easily torn apart by the tidal forces of larger neighbors. Each encounter strips away streams of stars, while the pressure from the hot intergalactic medium sweeps out the cold gas that fuels future generations of stars. Hubble's images capture this slow torture in haunting detail. Galaxies appear stretched and distorted, trailing immense streams of stars behind them like glowing contrails across the dark. Some are broken so thoroughly they can hardly be recognized as galaxies at all, reduced to ghostly clouds of starlight smeared across space. One of the most famous cases is NGC 4676, better known as the Mice. This system began as two spiral galaxies that brushed past each other around 160 million years ago. The gravitational pull warped their shapes into elongated forms, each trailing a narrow, sweeping tail that earned them their name. Yet the mice are only passing through one stage of destruction. Simulations reveal their long tails will eventually dissolve, their stars cast into the void, or drawn back into the surviving cores. In time, what remains will be two small elliptical galaxies, bearing little trace of their once splendid spiral arms. The violence extends beyond direct encounters. The cluster environment itself is hostile. The space between galaxies in these dense regions is filled with gas so hot, over 100 million degrees, that it acts like a relentless cosmic wind. As galaxies plunge through it, their reservoirs of cold, star-forming gas are stripped away. Together, harassment and gas stripping transform the character of clusters. Over billions of years, spirals vanish. Today, the densest clusters are dominated by massive ellipticals and small gas-poor systems known as dwarf ellipticals. The rare spiral galaxies that remain cling to the outskirts, where the forces are less extreme. This process has been ongoing for most of cosmic history, rewriting the population of galaxies across the universe. Many of the dwarf ellipticals we observe today are thought to be the battered remnants of once grand spirals, reshaped into submission by billions of years of violence. And yet, all of this destruction, all of this evolution, rests upon something deeper, an invisible framework that holds the universe together. Beneath every star and every galaxy lies the unseen skeleton of dark matter. It accounts for 85% of all matter, yet it cannot be seen. It neither emits, reflects, nor absorbs light. It is the ghost of the cosmos, revealed only through its gravitational fingerprints. Without it, galaxies could never have formed. Dark matter is the hidden skeleton of the universe. Just as bones shape the human body, dark matter provides the gravitational framework on which ordinary matter gathers, clumping into stars, galaxies, and the vast structures that stretch across the cosmos. Without it, the universe would be a smooth, featureless sea of gas. No galaxies, no stars, no us. The evidence is overwhelming. Astronomers studying the motions of stars within galaxies find they move far too quickly to be held by the gravity of visible matter alone. Galaxies should be flying apart, yet something unseen binds them. Clusters of galaxies offer even starker proof. When astronomer Fritz Zwicky studied the Coma Cluster in 1933, he realized its galaxies were moving so fast, the cluster should have scattered long ago. Something invisible, vastly more massive than all the stars combined, was holding it together. That something was dark matter. The only explanation was that the cluster contained far more mass than could be seen, hidden in an invisible form that astronomer Fritz named dark matter. Today, modern techniques allow astronomers to map this unseen substance across the cosmos using a phenomenon called gravitational lensing. Massive clumps of dark matter bend and distort the light of galaxies behind them, creating strange funhouse mirror effects that betray their invisible presence. These maps reveal a vast interconnected cosmic web. Dark matter forms sprawling filaments that stretch across billions of light years, connecting immense nodes where galaxy clusters take shape. Between these filaments lie enormous voids, regions of space nearly empty of both dark and normal matter. This web provided the very skeleton of the universe. It determined where galaxies would emerge, how they would gather, and the grand pattern of structure that fills the cosmos. On smaller scales, every galaxy sits inside its own dark matter halo, an invisible sphere of gravity that extends far beyond the stars we can see. Our own Milky Way lies at the heart of such a halo, one that stretches at least 600,000 light-years across, 3 times larger than the visible galaxy itself. This hidden sphere contains nearly 10 times more mass than all the stars, gas, and dust of the Milky Way combined. Computer simulations show what the universe would look like without it. A featureless sea of gas, too smooth to ever collapse into stars. The tiny density ripples after the Big Bang would have remained ripples forever. No galaxies, no planets, no life. And yet, despite decades of searching, we still do not know what dark matter actually is. Some theories suggest exotic particles that barely interact with normal matter at all. Others propose swarms of primordial black holes, ancient relics from the earliest moments of the universe. Or perhaps it is something stranger still, beyond our imagination. What we do know is this: dark matter shapes everything, and hidden within its colossal structures may be some of the most mysterious objects in existence: dark galaxies. These are vast halos of dark matter that never lit up. They contain the mass of billions of suns, yet shine with no light across any wavelength. They are invisible cities of gravity drifting through the void, detectable only through their pull on the cosmos around them. Computer models first predicted their existence. Most dark matter halos capture enough gas to ignite star formation, but some do not. Some remain silent, never gathering enough ordinary matter to spark their first stars. Detecting them requires detective work of the highest order. Astronomers search for their gravitational signatures, looking for the subtle distortions they leave in the light of distant galaxies. One of the most compelling candidates was found near the Virgo cluster, a massive structure containing around 1 billion solar masses, yet radiating no light whatsoever. It was discovered only because its gravity bent the path of background starlight, an invisible giant revealed by its shadow. But the mystery deepens. Why do these dark galaxies remain dark? In normal galaxies, dark matter halos gather gas, which cools and condenses into stars. The cycle of star formation then feeds on itself, with each generation birthing the next. Yet in these cases, something prevented the first spark. Perhaps the surrounding gas was too hot, energized by nearby galaxies or black holes, preventing it from settling. Perhaps these galaxies began to form, only to have their luminous matter torn away by violent encounters with larger systems. Whatever the cause, the result is the same. Immense dark matter skeletons adrift in silence, galaxies in everything but light. The most intriguing possibility is that dark galaxies represent an entirely different evolutionary pathway, one we still don't understand. Perhaps in certain corners of the universe, there are physical processes that stop ordinary matter from gathering inside dark matter halos. The result is ghostly, invisible galaxies that emerge naturally as the cosmos evolves. The James Webb Space Telescope is now beginning to pierce this mystery. With its unmatched sensitivity, Webb has revealed faint galaxies that older telescopes could never detect. Some of the so-called dark galaxy candidates are being reclassified as ultra-faint dwarf galaxies, just barely managing to form enough stars to glow in infrared light. Yet others remain completely dark, even under Webb's gaze. These confirmed dark galaxies are shaking our models of the universe. They challenge our assumptions about how dark matter and normal matter interact. They tell us that galaxy formation is far more complex and more varied than our theories predict. If a vast number of dark matter halos truly host invisible galaxies, then we've been undercounting the universe's structure on a massive scale. And what makes this even stranger is realizing that these hidden galaxies exist inside an even larger invisible framework, a cosmic web that stitches together everything we can see. Your place in the cosmos is not just Earth, not just the solar system, not even just the Milky Way. That's like saying you live in a house without mentioning the city, the country, or the continent. Your true cosmic address stretches further. The local group of galaxies, the Virgo cluster, and ultimately the Laniakea supercluster, a gravitationally bound region of over 100,000 galaxies spread across 520 million light-years. Only in 2014 did we discover Laniakea, whose name means immense heaven in Hawaiian. It's a fitting title for a structure so vast that light itself takes 500 million years to cross it. The discovery came by mapping the peculiar motions of galaxies, their deviations from the universal expansion caused by the tug of gravity. These flows revealed invisible rivers of matter, tracing the supercluster's true shape. The Milky Way, Andromeda, and tens of thousands of galaxies are all drifting together, pulled like water toward the great attractor at Laniakea's heart. This region, with the mass of tens of thousands of galaxies, is drawing our entire neighborhood at over 1,000 miles per second. Yet even Laniakea is not the end of the story. It too is flowing towards something larger, the Shapley attractor, 700 million light-years away. This creates a vast current of galaxies, a cosmic river streaming in one direction across distances so immense they dwarf everything we thought we knew about structure. At Laniakea's center lies the Virgo cluster, home to over 2,000 galaxies, including some of the largest ellipticals in the known universe. Its combined mass, around 1,000 trillion suns, makes it one of the most massive nearby structures, like threads in a vast invisible tapestry. Between them lie immense cosmic voids, regions so empty they span hundreds of millions of light-years. Our own local group of galaxies rests on one such filament, tethered to the larger cosmic web, but distant enough from the densest regions to avoid the chaos and destruction that unfold there. The scale of this structure is staggering. Laniakea, our home supercluster, is not an island but a single node in a far greater network of superclusters. The Perseus-Pisces supercluster, Hydra Centaurus, and dozens of others form a cosmic lattice stretching billions of light-years. Together they create a pattern, the cosmic web, that extends to the very edges of the observable universe. These superclusters are not scattered randomly. They're organized into enormous filaments and walls, some so vast they stretch for billions of light-years across space. Their existence challenges our understanding of how the universe evolved from the almost uniform conditions seen in the cosmic microwave background. The discovery of Laniakea revealed humanity's true place in this hierarchy. Not just as residents of a galaxy or even of a cluster, but as citizens of a cosmic continent bound by gravity into a single coherent whole. Yet even this immense supercluster is only a fragment of something far larger. The universe itself is a cosmic spiderweb, with filaments of galaxies and dark matter spanning distances so vast that entire superclusters appear as tiny ornaments on the strands. These filaments commonly measure 160 to 260 million light-years in length. That's so immense that light from one end to the other takes longer to travel than complex life has existed on Earth. And some filaments are far greater still. The Hercules Corona Borealis Great Wall, the largest confirmed structure in the universe, stretches more than 10 billion light-years. That's 1/10 the diameter of the entire observable cosmos. Even at the speed of light, it would take 10 billion years to cross. These colossal filaments are the backbone of cosmic architecture. They connect clusters and superclusters into a three-dimensional web that spans the universe. The pattern looks eerily familiar, like a neural network in the brain or the delicate structure of a living cell. Dense nodes of matter are linked by elongated strands, with vast empty voids separating them. The cosmic web traces its origins back to the first instant of creation. Tiny quantum fluctuations in the newborn universe were stretched to cosmic scales during inflation. Over billions of years, gravity amplified these tiny differences, funneling matter along invisible paths toward the densest regions. Dark matter led the way, clustering first, with normal matter following its gravitational blueprint to form galaxies and clusters along the filaments we observe today. The spaces between galaxies in these filaments are not empty. They're filled with the warm, hot intergalactic medium, a diffuse gas heated to millions of degrees. By earthly standards, it is almost nothing, barely matter at all, but spread across such unimaginable volumes. This gas contains more ordinary matter than all the stars in all the galaxies combined. Detecting these filaments is no easy task. The gas is too hot and thin to shine with visible light, and the dark matter is completely invisible. Astronomers reveal their presence by mapping the distribution of galaxies and by running computer simulations that trace the hidden dark matter scaffolding beneath. Another powerful technique is gravitational lensing. The combined pull of dark matter within a filament bends the light of background galaxies, distorting their shapes just enough to betray the filament's presence. With these methods, recent surveys have begun to map the cosmic web in unprecedented detail, showing filaments that span billions of light years, the great highways of matter that define the very shape of the universe. The cosmic web is not just a backdrop for galaxies, it is the stage on which their fates are written. Galaxies embedded within its filaments draw in a steady stream of fresh gas, funneled along the invisible highways of dark matter. This supply fuels star formation, keeping these galaxies alive and vibrant for billions of years. In contrast, galaxies stranded in the empty reaches of cosmic voids slowly starve, their gas exhausted, their stars fading into red embers. The web itself decides which galaxies flourish and which fade into silence. The largest filaments act as cosmic rivers, carrying thousands of galaxy groups and clusters along their flow. Even our own Milky Way, part of a modest local filament linking us to the Virgo cluster, is guided by these invisible threads. Though humble compared to the great filaments of the universe, our strand still spans tens of millions of light years, its gravitational pull shaping the motion of every galaxy caught within it. Simulations reveal that the cosmic web is not eternal. Dark energy, the mysterious force driving the accelerated expansion of space, will eventually tear its threads apart. Trillions of years from now, the filaments will stretch and fragment until each galaxy becomes a lonely island in an ever-expanding void. But for now, the web endures, weaving the grandest structures in existence, scaffolding so vast that they defy human imagination. Some of these structures are so immense that they seem impossible. The Sloan Great Wall, over 1.3 billion light-years across, ranks among the largest known. If the entire observable universe were shrunk to the size of Earth, this one wall would cover the scale of North America. Tens of thousands of galaxies line up within it, forming a sheet of matter that challenges the limits of cosmic growth. Yet even this titanic structure pales beside the Hercules Corona Borealis Great Wall. Spanning more than 10 billion light-years, it is a giant so colossal that astronomers question whether it should exist at all. To cross it at the speed of light would take nearly the entire age of the universe itself. These great walls form where multiple filaments converge, stacking galaxies into immense sheet-like structures. They act as the dividing walls between cosmic voids, like the soap bubble membranes of an incomprehensibly vast universe. Their discovery shook cosmology to its core. According to the cosmological principle, matter should be smoothly distributed on the largest scales. Gravity, limited by the speed of light, shouldn't have had enough time to shape such gigantic forms in a universe only 13.8 billion years old. And yet, they exist. Their very presence forces scientists to question the foundations of our models. Perhaps the early universe carried stronger density ripples than we thought, laying down seeds for such enormities. Or maybe exotic processes during cosmic inflation imprinted hidden patterns, guiding matter into these vast walls. Whatever the answer, the Great Walls are more than anomalies, they are clues. They hint at deeper truths about the universe, its beginnings, and the mysterious dark energy that drives its expansion toward eternity. The discovery of immense structures like the Great Walls places limits on the very nature of dark energy. Too much of it, and gravity would never have been able to weave galaxies into such colossal formations. Each new survey reveals another vast wall, another towering ridge in the architecture of the cosmos. The CFA2 Great Wall, first recognized in 1989, was the earliest hint that galaxies were organized on scales far larger than anyone had imagined. In 2016, astronomers uncovered the Boss Great Wall, stretching more than 1 billion light-years and filled with some of the most distant galaxies ever observed. These walls are not solid barriers. Instead, they are regions where galaxy filaments converge, billions of galaxies linked by invisible strands of dark matter, separated by immense regions of emptiness. Look closer and the structure reveals itself like a fractal. Galaxies fall into groups, groups form clusters, clusters connect by filaments, and on each level the pattern repeats. Cosmic architecture is layered, recursive, and endlessly vast. What we can see, the great walls within our observable universe, may only be local examples of a design that extends forever. If the cosmos is truly infinite, then the pattern of walls and voids could stretch without end in every direction. And between these giant walls lies an even deeper mystery: the voids. Cosmic voids are oceans of emptiness, expanses so vast and barren that they make the interstellar vacuum between stars seem crowded. Spanning hundreds of millions of light-years, they are the largest empty regions in the universe. The Bhuta's Void, sometimes called the Great Nothing, is one of the starkest examples. A sphere 330 million light-years wide, it contains almost nothing at all. Had the Milky Way formed in its center, the nearest galaxy would lie over 150 million light-years away, completely invisible to the naked eye, and hidden from discovery until only the most advanced telescopes of the modern age. To grasp the emptiness of such a place, consider this: the average density of matter across the universe is already minuscule, only about 6 hydrogen atoms per cubic meter. Within cosmic voids, that number drops to less than 1/10 of even this fragile average. These voids are emptier than the most perfect vacuums we can create on Earth. They are not scars from an explosion or cosmic accident. Rather, they are the quiet consequence of gravity's work. Regions that began with slightly less matter after the Big Bang were drained further as surrounding filaments and clusters pulled material away. The rich grew richer, the empty grew emptier, and even today, the process continues. Voids expand as matter flows outward into the walls around them. Over time, these voids will merge, leaving behind even larger regions of nothingness. And yet, the few galaxies that do live within voids are some of the strangest in the universe. Unlike their cousins in crowded clusters, void galaxies are often small, blue, and still forming stars at surprising rates. They should have long since consumed their gas, yet many continue to shine with new generations of stars. Perhaps, free from the stripping forces and violence of dense environments, they have kept their supplies of star-forming material far longer than expected. The largest known void, the giant void in the constellation Eridanus, is nearly 1 billion light-years across, an expanse of near total emptiness so enormous that it defies comprehension. These voids, as much as the walls and filaments, define the shape of the universe. They are the dark oceans between the islands of light, the empty silence that makes the cosmic web possible. The existence of such large structures places crucial constraints on how dark energy behaves, because too much dark energy would have prevented large-scale structure formation entirely. Galaxy surveys continue to uncover new examples of these immense cosmic walls scattered across the observable universe. The CFA2 Great Wall, discovered in 1989, was the first structure recognized to span hundreds of millions of light-years. Later, in 2016, the Boss Great Wall was found to stretch over 1 billion light-years and to contain some of the most distant galaxies ever observed. Each discovery deepens our understanding of the cosmic web's largest components. These walls are not solid barriers, but rather dense enhancements within the web, where galaxy filaments cluster together. They contain billions of galaxies connected by dark matter filaments, separated by vast cosmic voids. Their internal structure reveals the fractal-like, hierarchical nature of the universe. Within each wall, galaxies are organized into smaller groups and clusters, which in turn are linked by filaments stretching tens of millions of light years. Each level of magnification exposes a repeating cosmic architecture. Living within the cosmic web means that our observable universe may be only a small corner of a potentially infinite structure, extending endlessly in all directions. The great walls we can map could be just local examples of patterns repeating across a cosmos without bound. Even more striking is the realization that these massive structures exist beside vast, empty oceans of nothingness. Between filaments and walls lie regions so empty they make the space between stars appear crowded. These are cosmic voids, immense stretches spanning hundreds of millions of light years, almost entirely devoid of galaxies, stars, or even dark matter. One of the most famous is the Bhuta's Void, often called the Great Nothing. This spherical region measures roughly 330 million light-years across, yet contains almost no galaxies within its interior. Had the Milky Way formed inside its center, the nearest galaxy would lie over 150 million light-years away, invisible to all but the most advanced modern telescopes. From such a location, humanity might not have discovered other galaxies at all until the late 20th century. Voids are emptier than the best vacuums we can create in laboratories. While the average density of the universe is around 6 hydrogen atoms per cubic meter, voids fall to less than 1/10 of that. They didn't form by explosion, but by quiet neglect. They were regions slightly underdense after the Big Bang, and as gravity pulled matter into surrounding walls and filaments, these zones became progressively emptier. Simulations show they continue to expand, pushing matter away toward denser regions. Over cosmic time, voids will merge to form even larger expanses of emptiness. Yet even here, a few lonely galaxies persist. These void galaxies are puzzlingly small, blue, and actively forming stars, characteristics unexpected in such isolation. They should have exhausted their gas supplies long ago, yet many still produce stars at high rates. One explanation suggests that, sheltered from the violent interactions common in crowded clusters, these galaxies have managed to hold onto their gas for billions of years. The largest known example, the giant void in the constellation Eridanus, spans nearly 1 billion light-years across. Within it, smaller voids form a nested hierarchy of emptiness, echoing the layered clustering of matter in denser regions. Living inside such a place would mean a night sky stripped of wonder. Instead of thousands of galaxies visible through telescopes, there would be only a handful of faint smudges at the boundaries. The universe would appear barren, silent, and desolate compared to the vibrant richness we see from within our filament of the cosmic web. Voids are not just empty, they are essential. They provide the breathing room the cosmos needs to expand. As dark energy accelerates expansion, voids grow larger, while matter-filled filaments and walls become more compressed. Over trillions of years, the universe will become dominated by enormous voids, with all remaining matter confined to thin, fragile threads. Because voids contain so little matter, their evolution is governed almost entirely by the expansion of space itself. They serve as natural laboratories for probing the mysteries of dark energy and the large-scale structure of the universe. Yet even these vast deserts of nothingness exist within a cosmos defined by constant warfare. Between gravity and expansion, on scales of galaxies and clusters, unimaginable violence continues to unfold. Right now, 4 colossal galaxy clusters are colliding in the most violent cosmic event since the Big Bang. This cataclysm is taking place in galaxy cluster MAX J0717, located 5.4 billion light-years away. Each of the 4 clusters contains hundreds of galaxies, trillions of stars, and vast reservoirs of hot gas and dark matter. Their collision unleashes more energy than billions of supernovae detonating at once. These clusters are approaching one another at thousands of miles per second, accelerating quadrillions of tons of matter toward a titanic rendezvous that will reshape an entire region of space. Observations by the Chandra X-ray Observatory reveal their gas glowing at over 100 million degrees Fahrenheit, heated as shockwaves ripple outward for millions of light-years. What makes these collisions most fascinating is how they separate different kinds of matter. The diffuse hot gas collides, slows, and lags behind, while the dense galaxies themselves pass through with minimal interaction. Dark matter too behaves like the galaxies, feeling only gravity and streaming through unaffected. This creates eerie separations, galaxies racing ahead of their own clouds of gas, like runners leaving their shadows behind. Gravitational lensing maps show the dark matter stretching, distorting and twisting under the strain. Smaller galaxies are stripped and hurled into intergalactic space, while the heat released by these mergers suppresses galaxy formation across entire cosmic regions. Sometimes, the collisions are so perfectly balanced that clusters pass through each other completely, only to be pulled back together by gravity for a second violent crash. This process can repeat multiple times, creating a cosmic ping-pong effect that lasts for billions of years. One of the most dramatic and studied examples is the Bullet Cluster, where two galaxy clusters collided at such extreme speed that their hot gas was violently stripped away and completely separated from their galaxies and dark matter. The resulting structure provided some of the strongest evidence yet for the existence of dark matter, since gravitational lensing revealed that most of the mass was associated with the galaxies rather than the displaced gas. Computer simulations of such colossal collisions reveal their astonishing complexity. These events unfold over hundreds of millions of years through repeated phases of approach, impact, separation, and recollision. Each phase unleashes different processes: shock heating of gas, tidal stripping of galaxies, and the creation of massive, radio-emitting structures that stretch across intergalactic space. The violence also sparks intense bursts of star formation. As shock waves ripple through galaxies, gas clouds are compressed, igniting stellar nurseries on an extraordinary scale. Some of the most luminous galaxies ever observed lie within colliding clusters. Their star formation rates hundreds of times greater than those of ordinary, isolated galaxies. These cosmic battles represent the final stages of large-scale structure formation. With dark energy accelerating the expansion of space, galaxy clusters are drifting farther apart, becoming more isolated. Eventually, the age of major cluster collisions will end, leaving behind a universe of lonely clusters surrounded by ever-growing voids. Yet the drama of collisions is only part of a much larger cosmic ecosystem, one hidden from our eyes until recently. Between every galaxy in the universe flows a vast network of gas, cosmic rivers of plasma so hot that the surface of the Sun would feel cool in comparison. The intergalactic medium reaches temperatures above 10 million degrees Fahrenheit, stripping atoms of their electrons and leaving behind a seething sea of bare nuclei and free electrons. This plasma is so diffuse, it would be considered a perfect vacuum on Earth. Yet in total, it contains more normal matter than all the stars in all the galaxies combined. It threads the universe along dark matter filaments, forming a kind of cosmic circulatory system. Like blood through arteries, it carries matter and energy across billions of light years, feeding galaxies and clusters with the raw materials needed for growth. The extreme temperatures of this medium are a direct result of cosmic gravity. As matter falls into dark matter filaments, it compresses and heats, just as air grows hot when compressed in a bicycle pump. Only here, the process drives temperatures to millions of degrees. Supernova explosions add to this heating, blasting material outward at thousands of miles per second. These blasts spread heavy elements forged in stellar cores into the cosmic web, enriching the intergalactic medium with the seeds for future generations of galaxies. Despite its importance, this vast reservoir is nearly invisible to the human eye. Hot plasma emits little light at visible wavelengths, making it undetectable with ordinary telescopes. Instead, astronomers rely on X-ray observatories that capture the high-energy radiation produced when electrons in the plasma interact with powerful magnetic fields inside galaxy clusters. In recent years, these efforts have revealed immense bridges of hot gas spanning hundreds of millions of light years, connecting clusters across the cosmic web. The Planck satellite maps some of these structures by detecting the thermal Sunyaev-Zeldovich effect, in which photons from the cosmic microwave background gain energy as they pass through the hot plasma. But perhaps the most striking breakthrough has come from fast radio bursts, brief, mysterious flashes of radio energy from distant galaxies. These cosmic use state. This solved a decades-old riddle known as the missing baryon problem. Theoretical models of the early universe predicted exactly how much ordinary matter should exist, based on precise measurements of the cosmic microwave background, the faint afterglow of the Big Bang. The number was clear: normal, or baryonic matter, should make up about 5% of the universe's total mass energy. But when astronomers searched for it in stars, planets, gas clouds, and galaxies, they consistently came up short. Half of it was missing, seemingly erased from the cosmic census. The answer was far stranger. The missing matter was never gone. It had been hiding all along, stretched thin across the cosmic web in vast, invisible rivers of superheated plasma. Too diffuse to see directly, yet too abundant to ignore, it was finally revealed thanks to the unique properties of fast radio bursts. These cosmic lighthouses last only milliseconds, yet in that blink of time release more energy than the sun generates in a whole day. When their signals cross the cosmic web, they scatter and disperse in ways that betray the presence of ionized hydrogen, the building blocks of ordinary matter. By tracing dozens of bursts from known distances, astronomers calculated the number of electrons encountered along each path. This number pointed directly to the hidden mass of the universe. The solution was definitive. The missing baryons reside in the warm, hot intergalactic medium, gas heated to temperatures between 100,000 and 10 million degrees Fahrenheit. This material is so incredibly thin that a volume equal to Earth's entire atmosphere would contain less matter than a single breath of air. And yet, when spread across the incomprehensible spaces between galaxies, it adds up to half of all the ordinary matter in existence. This was more than a triumph of clever observation. It was the resolution of one of astronomy's deepest puzzles. It showed how matter is apportioned across the cosmos. About 5% of the universe is ordinary matter, split evenly between stars and galaxies on one hand, and the hot intergalactic plasma on the other. The rest is composed of dark matter and dark energy, mysteries that remain unsolved. But the discovery also revealed something profound about the way galaxies live and die. This intergalactic reservoir is not just a hiding place, it is a regulator. Galaxies can draw from it, siphoning gas to spark new generations of stars. Yet because the gas is so hot, it resists capture, forcing galaxies to evolve more slowly. Like a cosmic thermostat, the warm, hot medium governs the pace at which galaxies grow, ensuring that they neither burn out too quickly nor balloon uncontrollably. The missing baryons were never truly missing. They were the hidden lifeblood of the universe, quietly shaping the evolution of galaxies over billions of years. Computer simulations now factor in the presence of this hot intergalactic medium when modeling the birth and growth of galaxies. The results reveal something profound. Galaxies and the intergalactic medium are locked in a constant dialogue. Gas flows in, fueling star formation, while feedback processes push matter back out, regulating their growth across cosmic history. Without this delicate balance, galaxies would either burn out too quickly or balloon into giants that shouldn't exist. Yet even as we account for normal matter, we're reminded of how little we truly know. Dark matter and dark energy still dominate, making up a staggering 95% of the universe. Forces that remain almost entirely mysterious despite decades of research. This fog of missing matter, now found, weaves through the entire observable universe like invisible rivers of fire, connecting galaxies in a web of superheated plasma. And that observable universe itself has limits, boundaries that mark the edge of human knowledge. To glimpse what lay beyond our sight, astronomers turned to the Hubble Space Telescope. They aimed it at what seemed to be the emptiest patch of sky imaginable, a darkness smaller than a grain of sand held at arm's length. For over 11 days, Hubble stared into the void, gathering faint whispers of light. The result was breathtaking. That empty patch bloomed into the Hubble ultra-deep field, revealing 10,000 galaxies scattered like jewels across billions of years of cosmic history. Nearly every speck of light in the image was not a star, but an entire galaxy, each one holding billions of suns, planets, and perhaps civilizations we will never know. The image became a cosmic time machine. The nearest galaxies appeared as they were millions of years ago. The most distant revealed the universe when it was less than 1 billion years old. Its first pioneers, fragile and irregular, packed with young blue stars forming at furious rates. Others showed mature spirals and ellipticals, shaped by eons of mergers and cosmic violence. And the most staggering revelation, that single patch of sky, just a fraction of the heavens, suggested something astonishing. If every tiny region of space holds 10,000 galaxies, then the observable universe contains trillions. Follow-up observations went even deeper. The Hubble Extreme Deep Field combined years of data to peer further back in time than ever before. revealing galaxies that existed when the universe was only 400 million years old. These were true cosmic infants, the first stellar nurseries just beginning to push back the ancient darkness. But even Hubble had its limits. The James Webb Space Telescope, with its powerful infrared eyes, has surpassed those achievements, reaching galaxies that formed just 280 million years after the Big Bang. Webb continues to find more galaxies in places we once thought were completely empty, proving the early universe was far more crowded and active than we imagined. What makes these deep fields so powerful is their honesty. They don't target one special object. Instead, they capture the universe as it really is, a random slice of the cosmos, filled with galaxies of every shape and age. They provide a true census of creation, showing us how galaxies of all kinds populate the universe across time. And within these images, the cosmic web comes alive. Galaxies are not scattered randomly, but drawn together along invisible filaments of dark matter, leaving behind vast cosmic voids. Even across billions of light years, we can see this hidden scaffolding shaping the universe. Each galaxy revealed in these fields is a unique experiment. Some are isolated giants, while others crowd together in clusters, their shapes warped by violent encounters. Spirals are shredded into ellipticals, galaxies merge and collide, and entire families of stars are born and destroyed. These images are living laboratories, letting astronomers test theories of galaxy evolution and compare them against billions of years of reality. And yet, even these deepest images only show a fraction of what lies beyond. Farther still is a boundary we can never cross, our cosmic horizon. This isn't a wall of matter, but a wall of time. Light simply hasn't had enough years to reach us from beyond. At that edge lies the cosmic microwave background, the faint afterglow of the Big Bang itself. It is the last light we can ever see from the moment, 380,000 years after creation, when the universe cooled enough for protons and electrons to combine into atoms. Before that, space was opaque, filled with free electrons scattering light endlessly, like the inside of a star. When recombination happened, photons were released at last, flooding the cosmos with the first true light. That ancient glow marks the ultimate limit of our vision. Beyond it lie the cosmic dark ages, when the first stars were forming, but their light was smothered by neutral hydrogen fog. We will never see through that veil, not because our telescopes aren't powerful enough, but because light itself cannot cross that boundary. From Earth, the observable universe stretches about 46.5 billion light-years in every direction, a diameter of 93 billion light-years, larger than its age suggests, because space itself has been stretching like a cosmic conveyor belt. Light, we see today, began its journey when galaxies were much closer, but the expansion of space has carried them farther and farther away as their photons streamed toward us. This expansion creates another sobering truth. Some galaxies we see today are already lost to us. Their light from long ago still reaches Earth, but the galaxies themselves have drifted beyond our future horizon. Any light they emit now will never reach us, carried away by an expansion faster than light itself can travel. The cosmic microwave background is often called the baby picture of the universe. Frozen in that faint afterglow are tiny ripples, minute temperature fluctuations that carry the fingerprints of everything to come. These subtle variations, born from quantum fluctuations during the mysterious era of cosmic inflation, were stretched across space itself and later amplified by gravity, seeding the galaxies, clusters, and cosmic web we see today. Modern satellites like Planck have mapped these ripples in exquisite detail, extracting the blueprint of the cosmos with astonishing accuracy. From them, we've measured the universe's age, composition, and geometry. We know it is flat, and that it is made of just 5% normal matter, 27% dark matter, and nearly 70% dark energy. Yet hidden in these maps are tantalizing hints of something beyond. Structures and variations too large to fit within our observable horizon. They whisper of regions that may be radically different from our own. Here lies one of the most profound possibilities, that our universe may not be the universe at all, but merely one bubble in an endless multiverse. Perhaps space is infinite, stretching forever with infinite galaxies, infinite stars, and infinite copies of every possible arrangement of matter, including you, sitting here, hearing these words. In such a cosmos, every decision you did or didn't make exists somewhere. There are Earths where dinosaurs never fell, where entire histories played out along alien timelines. Infinity guarantees not only endless repetition, but endless novelty. Even if we remain confined to our own bubble, we already know this truth. Our observable universe is but a fraction of reality, a finite island in an infinite sea. And yet, this limitation doesn't diminish the wonder of what we can see. Within our horizon, we've traced the story of 2 trillion galaxies, stretching across 13.8 billion years of cosmic history. From the smallest proto-galaxies lighting up the ancient dark, to giant clusters colliding in cataclysmic violence, to the elegant spirals and ellipticals that crown the present era. The same forces shape them all. Those same forces shaped us. The carbon in your cells, the oxygen you breathe, the iron in your blood, all were forged in the fiery hearts of stars that lived and died long before Earth was born. You are, in the truest sense, made of stardust, and yet the cosmic perspective cuts deeper still. If there are 2 trillion galaxies, each with hundreds of billions of stars and untold trillions of planets, then the odds of life beyond Earth approach certainty. Somewhere, life must have stirred as it did here. Perhaps it flourished, perhaps it ended. But across distances so vast that communication is nearly impossible, we remain both part of an infinite cosmic community and utterly alone. This paradox defines our place. We are tiny, fragile beings on a pale blue dot, orbiting an ordinary star in an unremarkable arm of a typical galaxy. Our conflicts, our wars, our borders, all of them shrink to near absurdity against the backdrop of galaxies colliding over eons. Civilizations rise and fall in the blink of a cosmic eye. But that same perspective reveals how rare, how precious Earth truly is. In a universe dominated by dark matter, radiation, plasma, and violent extremes, a planet that nurtures life is not ordinary. It is extraordinary. Here, after billions of years, the universe evolved a way to look back on itself. Through us, it thinks, wonders, and dreams. Every telescope image, every scientific breakthrough, every moment you look up at the stars in awe, it is the cosmos reflecting on its own existence. We are the eyes of the universe, the brief flicker of consciousness in an ocean of matter and light. And though our time may be short compared to the endless expanse, our awareness makes us immeasurably significant. We are the way the universe knows itself. This realization carries profound responsibility. We are the only known beings capable of preserving and transmitting cosmic knowledge across generations. The story of the universe, from quantum fluctuations in cosmic inflation to the formation of 2 trillion galaxies, exists in its full glory only within human consciousness. And the scientific records we create, our cosmic journey through every galaxy in the observable universe, reveals that we live in an age of unprecedented discovery. Never before in human history have we been able to see so far into space and time, to understand so much about our cosmic origins and destiny, or to appreciate the true scale of the universe we inhabit. The James Webb Space Telescope and future observatories will continue pushing back the frontiers of knowledge, revealing new types of galaxies, new cosmic phenomena, and deeper insights into the fundamental nature of reality. Each discovery adds another piece to the cosmic puzzle, bringing us closer to answering the ultimate questions about our existence and purpose. Yet perhaps the most important lesson from our journey through 2 trillion galaxies is that the universe is far stranger, more beautiful, and more awe-inspiring than we ever imagined. From dark matter scaffolding to galactic cannibalism, from impossible early galaxies to cosmic web filaments spanning billions of light years, reality consistently exceeds the limits of human imagination. We end where we began, as temporary arrangements of atoms in an infinite cosmos. But now, with the knowledge that we are participants in the most extraordinary story ever told, the evolution of the universe itself, from simplicity to complexity, from darkness to light, from unconscious matter to conscious beings capable of contemplating their own cosmic significance. In the end, flying through every galaxy in our observable universe brings us home to Earth with a deeper appreciation for both our cosmic insignificance and our cosmic importance. We are small, temporary, and isolated in space and time, but we are also the universe's greatest achievement. matter organized in such a way that it can understand its own existence and contemplate the infinite mystery that surrounds us on all sides.